Section 15.2. The particle in a one-dimensional box. In this section, we confine a particle inside this box from 0 to A. This is a one-dimensional box, so really it's actually a line. The particle can move on the line between 0 and A. What about the vertical axis? It's actually the potential energy of the particle. The potential energy of the particle is 0 inside the box. It's infinity outside the box. Therefore, this particle is completely confined between 0 and A. Now let's write out the time-independent Schrodinger equation for this particle. Well, it should be h psi equals E psi, and h is the sum of the kinetic energy operator and the potential energy operator. But inside the box, the potential energy is always 0. Therefore, we just need to write out the kinetic energy operator here. We apply the kinetic energy operator to psi. The result is E psi. We learned this equation in section 15.1. The general solution is a linear combination of e to the power of plus ikx and e to the power of negative ikx. What is k? K is the square root of 2me over h bar. So really, k is the magnitude of the momentum over h bar. K times h bar is the magnitude of the momentum of the particle. Now, because this wave function must be single-valued at the boundaries of the box, so outside the box, psi is 0. Over here, psi is 0. Therefore, at x equals 0 and x equals a, the value of the wave function has to be 0, just to make sure the value is single-valued here and here. And also, we'll have to make sure this wave function is continuous. So again, if it's 0, the value of psi is 0 here, then it has to be 0 at this point. If the value of psi is 0, when x is greater than a, then this psi has to be 0 at this point to ensure this wave function is single-valued and continuous. Now we have two so-called boundary conditions. We know psi of 0 is 0. So we just plug in x equals 0 here and here. And then we know the sum is going to be 0 when x is 0. So we get this equation. E to the power of 0 is 0. So we know a plus a minus is 0. Therefore, this a minus is negative a plus. This wave function can be rewritten in this format because a minus, a sub minus, is negative a sub a plus, negative a sub plus. Now we can combine this a plus, so it's here. We have e to the power of positive ikx minus e to the power of negative ikx here. Now I divide this by 2i and multiply this a plus by 2i. The reason I do this is because this expression inside the parenthesis is simply sine kx. Remember, e to the power of I theta is cosine theta plus I sine theta. E to the power of negative I theta is cosine theta minus I sine theta. So you are looking at, over here, you are looking at cosine kx plus I times sine kx. And this one is cosine kx minus I times sine kx. You do the subtraction, you get 2i times sine kx. And 2i times sine kx divided by 2i is sine kx. Therefore, this wave function of the particle inside the box is got to be a sine function. For simplicity, we set a to be 2i times a plus, because a plus is an arbitrary number. This a is also an arbitrary number. And then psi x is simply a constant times sine kx. Now, the second boundary condition. Psi of A is 0. So we plug in this psi of A is 0 here. So A times sine Ka is 0. We have this equation. Now let's analyze this equation. Either A is 0 or sine Ka is 0. But A, this uppercase A, cannot be 0. This A is the normalization factor. This A ensures the integral of the squared modulus of psi is 100% inside the box. All right, because again, the integral of this squared modulus of psi is the probability. The integral from 0 to A of this psi squared should be 100% because we have 100% probability of finding the particle inside the box. All right, so this normalization factor cannot be 0. Therefore, the sine Ka has to be 0. How can you have a sine function of Ka to be 0? Well, Ka can be 0. Sine 0 is 0. We know that. Sine pi is 0. Sine 2 pi is 0. Sine 3 pi is 0. Sine 4 pi, sine 5 pi, sine 6 pi is 0. So really, as long as this Ka is n pi, we have this psi of A equal to 0. Therefore, we know Ka is n pi, and then n must be an integer. N has to be 1, 2, or 3, or 4, etc. All right. Now we replace this K with n pi over A. So K is n pi over A. We get this equation. The wave function of the particle inside the box is the normalization factor A times a sine function of n pi x over A. Again, this n pi over A is K. N has to be integer. But wait, can this n be 0? The answer is no. If n is 0, then psi is 0 inside the box, everywhere inside the box. So again, if n is 0, you have sine 0. When you have sine 0, no matter what the value of x is, sine n pi x over A is always 0 if n is 0, right? So that means there's no particle in the box. Okay? So n has to be a positive integer. N cannot be 0. As long as n is a positive integer, this function is going to be 0 at two positions. When x is 0, when x is A, this function, this wave function is 0. This is to ensure this wave function is single valued and continuous at the two boundaries. However, as long as n is positive integer inside the box, the value of this sine function is not necessarily 0, and it's possible to have a non-zero psi. That means the squared modulus of this psi is going to be positive, and that means we have a positive probability of finding a particle inside the box, and that probability should be 100%. Okay, now let's look at the wave function. Basically, it's a sine function of n pi x over A, and if you just look at this equation, you can plug in n is 1 or 2 or 3 and 4 and plot this function. So maybe I should put the equation here. Just to remind you, this is the wave function, so that you can see, look at the picture here. When n is 1, we have sine pi x over A. Don't worry about the normalization factor. It's just a constant. It determines the magnitude of the wave. But for now, let's just focus on the sine function itself. When n is 1, so we have sine pi x over A. So when x is 0, the function is 0. When x is A, we have sine pi. It's also 0. When x is 1/2 of A, you have sine pi times 1/2 of A over A. That's sine 1/2 of pi. Sine pi over 2 is 1. That's the maximum value of the sine function. So we have a maximum here, and Also, you can see when x is between 0 and a, we are looking at sine pi times x over a. It's going to be sine 0 to pi, so the angle is between 0 to pi. It's always positive inside the box. All right, what if n is 2? If n is 2, you're looking at sine 2 pi x over a. Okay, sine 2 pi x over a. If you think about sine 2 pi x over a, this function is going to be 0 when x is 0, when x equals a, and also when x is 1/2 of a. So again, sine 2 pi times 1/2 of a over a is sine pi. Sine pi is 0. What if n equals 3? When n equals 3, plug this in, you have sine 3 pi x over a. Now, when x is 0, 1/3 of a, 2/3 of a, or a, this sine function is 0. So in this case, we can say there are 2 nodes inside the box. When n is 4, there are 3 nodes inside the box. The positions of the nodes are 1/4, 2/4, and 3/4 of a, or 1/4, 1/2, or 3/4 of a. So now let's look at this 4 solutions. Again, with n equals 1, 2, 3, 4. There's 0 node inside this box when n equals 1. 1 node, 2 nodes, 3 nodes. Really, the number of nodes inside the box is this quantum number n minus 1. And also you can tell, as n increases, the number of nodes increases. Also, the energy increases. You learned this, I think, in organic chemistry. When you have an anti-bonding orbital versus a bonding orbital, let's make it simpler. Let's just look at an anti-bonding sigma versus bonding sigma. In the bonding sigma orbital, there's no node. When you look at this anti-bonding sigma, there's 1 node. The more node you have in the molecular orbital, the higher energy this orbital has. Same here, actually. If you look at the quantum numbers, when n increases, the number of nodes increases, and also the energy increases. All right, now let's look at the normalization factor A, uppercase A. The probability of finding a particle between 0 and a should be 100% because it's fully confined. So we have this equation. On the left-hand side, this is the physical meaning of this integral is the probability of finding the particle between 0 and a. This has to be 1. And then we plug in the expression of psi, which is uppercase A times this sine n pi x over a squared. And a is a constant, so we took it out of the integral. And this function is a sine function squared. If you're familiar with trigonometric functions, sine theta squared is actually 1 minus cosine 2 theta over 2. So over here we have this. We can prove this easily, but I don't think I'll do that here. You can just Google this. Again, sine theta squared is simply 1 minus cosine 2 theta, and then divided by 2. All right? Okay, so we can easily integrate this 1/2. That's easy. We can integrate a cosine function. This is also trivial. You'll see this integral is actually 0 in the end. The integral of 1/2 is 8 over 2. All right, so over here, this is how I integrate this cosine function. I did some variable substitution here. I said, z or whatever dummy variable to be 2 n pi x over a. So you're looking at cosine z dz over here. And cosine z dz, how do we integrate that? It's very simple. It's just sine z. You just need to change the lower and upper limits for z correspondingly. So if z is defined this way, you just plug in x equals 0 here. So z is from cosine 0 to cosine, you plug in a here, 2 n pi. Cosine 0 is 1. The integral of this is a sine function. It's going to be sine 2 pi x over a. So you plug in x equals 0, you get sine 0. You plug in x equals a, you get sine 2 pi times a over a. That's sine 2 pi. Sine 2 pi is also 0. So if you look at this integral, again, it's going to be 0 minus 0. It's going to be sine 2 pi minus sine 0. Okay, so we have this a squared times just 1/2 to be 1. Oh, actually, in this document, I set this phi to be 2 pi x over a, but this is a dummy variable. You can use any variable here, z or phi or beta or whatever. So really, n squared times this lowercase a over 2 is 1. A is the square root of 2 over a. So this value ensures the wave function is normalized. Normalization means the total probability of finding the particle in the entire space is 100%. Because the particle cannot appear outside the box, that means, well, the probability of finding the particle between 0 and 1 should be 100%. This is the so-called normalized wave function for the particle in the box. Again, normalization means we need to ensure the total probability of finding a particle in the entire universe is 100%. Just remind you, n is a positive integer. X is the position of the particle. So really it tells you this particle can be anywhere between 0 and a. Just not at 0, not at a. But it can be anywhere between 0 and a. All right. Now we're going to apply the kinetic energy operator to this wave function to find its kinetic energy. So this is just simple mathematics. As long as you know how to take the second derivative of a sine function. The first derivative is of sine theta is cosine theta. The second derivative of sine theta is negative sine theta. And then you need to use the chain rule and then realize that n pi over a should be squared here. And you need a negative sign here. So this is just a simple differential calculus. When you do that, you see a bunch of terms, but realize this. Square root of 2 over a and this sine function together is the original wave function sine. So I put them together, okay? And I put all those other terms together. We have this. So really it's a constant times sine. The constant is n squared, h squared, over 8ma squared. What's the physical meaning of this? So first, we realize that this psi is an eigenfunction of the kinetic energy operator, because after we apply the kinetic energy operator to psi, we get this, the result is psi multiplied by a constant. So psi is an eigenfunction of the kinetic energy operator, and this constant, this eigenvalue, is the kinetic energy. So again, this is the kinetic energy. And in this case, it's also the total energy, because remember, the potential energy of the particle inside the box is 0. Again, this is the kinetic energy and also the total energy. Now, if n is 1, we have the lowest possible energy. It's h squared over 8ma squared. What's the second lowest energy? It's 4. It's 2 squared times h squared over 8ma squared. The third lowest energy is 3 squared times h squared over 8ma squared. Now, given this expression for the total energy and kinetic energy, we can calculate the momentum of the particle. This is the magnitude of the momentum. Momentum is mv. This is just m squared over the square root of m squared v squared. And we can write this in a different format. It's 2m times half mv squared, and this is just the square root of 2me. This is actually the kinetic energy. This is the total energy, but they are the same in this case. All right, we plug in the expression of the total energy n squared, h squared over 8ma squared, and then m and m cancel. We have n squared, h squared on top. We have 4a squared on the bottom, and then we take the square root. The result is nh over 2a. So the magnitude of the momentum is nh over 2a. We don't really have to solve the Schrodinger equation to get the momentum of the particle. We learned the de Broglie equation. The magnitude of the momentum is just h over lambda. And then we know what the lambda is by looking at the pictures of the wave functions. Look at this. For this function, we are looking at 1/2 of the wavelengths, right? And this is one wavelength. Well, this one maybe 1.5 wavelengths. This is 2 wavelengths. So in this case, A is equal to 1/2 of the wavelengths. In this case, A is 1 wavelength. In this case, A is 1.5 wavelengths. In this case, A is 2 wavelengths. So in this case, wavelength is 2 times A. In this case, wavelength is A, or 2A over 2. In this case, the wavelength is 2A over 3, 2/3 of A. So this is the wavelength. In this case, the wavelength is 2A over 4. So really, the wavelength is 2A over n. N is the quantum number. All right. So now let's get back to the de Broglie equation. Lambda, the wavelength, is 2A over n. So the momentum is h divided by 2A over n is nh over 2a. This expression is exactly same as this equation. All right. So again, if we have a particle in the box, it has a wavelength. The wavelength depends on its quantum number. All right. The wavelength is 2A over n. And we know how to determine the magnitude of its momentum. It's nh over 2a. However, we don't know anything about the sign of the momentum. P can be plus minus nh over 2a at the same time. So this particle can be moving towards left and right at the same time. Now again, let's review the shape of psi. This is the shape of psi. When a equals 1, there's 0 node. When a equals 2, there's 1 node. A equals 3, 2 nodes. A equals 4, 3 nodes. So all our sine functions, the sine function is sine n pi x over a. And this is the squared modulus of psi, therefore they are all just positive. But still, you can see the node here, here, and here, and here. The number of nodes is, again, equal to n minus 1. What's the physical meaning of this squared modulus of psi? Probability density. Probability density. So if we multiply this by dx, that will give us the probability of finding the particle between x and x plus dx. And then if we integrate the squared modulus of psi dx from 0 to a, and then the integral should be equal to 1, 100%. Alright, so we can also determine the spacing between any two energy levels because we know the energy of level n is n squared h squared over 2ma squared. So if we are looking at a transition of a particle from level 1 to level 2, the excitation energy is simply the difference between this energy and this energy. We plug in these two quantum numbers, 2 and 1, we get 3h squared over 2ma squared. Why is this important? Well, just imagine a situation. A particle in level 1 absorbs a photon and gets excited to level 2. Now we know how to calculate the energy of the photon and, of course, the frequency and the wavelength of the photon. Another example, 5 to 6 transition. We plug in 5 and 6. 6 squared is 36. 5 squared is 25. So we know the excitation energy is 11h squared over 8ma squared. Again, if this transition is induced by a photon, you're looking at the photon energy right here. And also you can easily determine the wavelength and frequency of that photon. So really, you are looking at one theoretical method to compute the UV-vis spectrum of some chemical systems that contain electrons that behave like particle in a box. Now let's get more general here. Let's say we're looking at from n to n plus 1 transition. So we plug in n plus 1 squared, n squared here. The result is this. N plus 1 squared is n squared plus 2n plus 1.